Well, I mean, there's like 50-50 that he comes down.
That's true.
He's not the only one missing. He's not the only one missing.
He's not, but I know where Abraham is. He's actually working on something.
Maybe not.
Yeah.
Maybe. I'm like pretty sure this is his first class.
I was, like, what?
Pretty sure this is his first class today.
We're talking about you, Vincent.
And I heard him.
We miss you. Why don't you come to class? All right, my friends, let's get rolling. We got a really big day today, and we've got a very different homework assignment. It's not Connect. So Kate, you'll like this. It's not a Boolean setup where you either get it right or you don't, and then redo the whole thing. You're gonna like this. All right. Yeah. Oh, I closed the boy. Now they'll have to make a scene when he comes in. Okay, whatever. Alrighty, friends, we're talking about our last method of proof, and I think you're gonna like this one. So, okay, let's close the laptops, unless we're taking notes with them, which I think Cadence might be. Thank you. Awesome. Great. So, we are, because you really want to pay attention to this today, because I'm going to ask you to do it over the weekend. So over the weekend, I'm gonna have you write some proofs, and you're gonna bring them in, you're gonna I've got some stuff for you. So let me actually give you your assignment right now before I forget. Yep, that's right. Some serious shit. So,
actually paying attention.
due Monday. So I'll collect at the start of class. And I'm not gonna ask like that you're perfect, and Alex, you got classes, man.
Yeah, you said we gotta actually pay attention, so I'm trying to.
Oh my God. Wait, so normally it's just like a fuzz in here, and you're just like kicking back.
You can't see the word at all.
Wait, oh yeah. Okay. Everybody wears glasses normally, and today they put them on because I said to pay attention.
No one's been paying attention to all of you all.
Like
No one
a
can
low
see.
res class. Okay, so I want you to prove that 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 times 2n plus 1 over 6. So, using mathematical induction, which is what we're going to talk about today. And I'm going to put some caveats on this, because I don't actually expect you to have a beautiful proof or anything. It's going to be like first draft, using mathematical induction. So, what I need from you is write a nice first draft. It doesn't have to be right. You have to show me that you put the effort in, right? And do what we're going to do today. And so, like, kind of doing a facsimile of the outline I'm going to show you today. Write a nice first draft. Make a copy to hand in. So this part scares the hell out of me. Hand in, because when I ask folks to like staple stuff, like inevitably someone will be like, "Come to class, I don't have a staple." Well, guess what? I don't have a copier. So I definitely do not have a copy of the thing I'm asking you to do, because I want you to have a copy and me to have a copy. One's to turn in, and then one is to keep for you. So, and there's a copy machine right over there. So I'm like giving you all the info you need to do that. A nice first draft, and then we'll do some revisions. So Monday I'm gonna like go around and consult with everybody and let you know what's up. And then I'm gonna give you another problem to do for Wednesday. Okay, so that's your assignment. I don't know why I have 1 on there. 1, 2, done. Hand it in. So, start of class. That's what will get you the credit. This is for the credit class. We will revise together. Revise and consult together. And a new problem will be handed out. Okay, is everybody clear on what I'm looking for here? And check out, there's a key word here.
Nice.
Yeah, nice. Nice. Yes,
What does
Al?
like the dot 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 in the middle mean?
Oh, cool. That's a great question. That is, this means continue on with the pattern. So, for example, it's saying that there's a rhythm set up here, Alex, and the next thing in line, what would be the next thing in the sum?
4 squared?
4 squared.
Okay.
And if n was 4, you'd be done. What if n was 5 squared? Well, then you'd have
Oh,
3
so you
squared.
go up until n. Oh, okay.
Yes, sir.
Okay.
Yeah, a great question. Yeah, thanks for asking that. Did I start recording there?
Yeah.
Thank you. Beautiful. Okay, so my friends, let's get rolling. We do have to get through all this today. So the goal of mathematical induction. So mathematical induction, our last proof method. And like I said, I really think it's the most accessible because it's really well defined what has to happen here. So this is a proof method, and this will probably be a method you see an awful lot in computer science. A proof method to demonstrate the truth of a statement of the form P of n for n greater than or equal to b, where n and b are integers. And let's actually put in front of here, just to add this, I would add this statement, prove P of n. There we go. And this will probably make more sense as we see some examples. I've got a bunch of examples we're going to work through together today, and maybe even have some time to start on what I'm asking you to do. I'm going to do one just like this as our very first example. So our first example, bless you. Example. Prove 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. So go ahead and write that down, and let's talk about what I just wrote. And I want to address Alex's awesome question from before about what's going on here. So what we're trying to do here is establish an entire collection of formulas. So for example, this thing is the general case of specific versions. Specific, let's see if I can spell that. Specific cases. So for example, if n equaled 5, what this statement means is that 1 plus 2 plus 3 plus 4 plus 5. Notice how n is 5, and I'm running the sum all the way up to that n. So is that making a little more sense now, Alex?
Yeah, that makes
Okay,
sense.
fantastic. So to do that sum, to actually add up all those numbers, I don't have to add them up. I can use this formula instead. So this formula says replace this n with 5, this n with 5. So I've got 5 times 6 over 2. And if I simplified that, that would be 15. Does that sound good? It's 30 on top over 2. 5 times 6 over 2. So this is a... Heard... Wait a minute. Oh, that was just the wind. I thought it was Vincent, but it was just the wind. Thought you sailed in on a ship. All right. So, if n equaled 10, oh my gosh, then we've got this huge, I'm not going to write them all out, but I want to explain this notation. Notice that the thing before this would be 9 and then 10. To crank out that sum, all I have to do is multiply 10 times 11 and divide by 2. So that turns into 5, excuse me, I should say 1 there. Got a little excited. So that's 55. Is the sum of all those numbers. So it's kind of a cool formula because instead of having to like, on my calculator, blah, 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 I can just use that elegant formula. These cases, you could even do that, but good Lord, what if I had n equaled 1,000? And I said to you, hey, what's the sum of the first 1,000 integers? The first 1,000 whole numbers? And you would, hopefully you wouldn't get out your calculator and start wasting your life by adding up those 1,000 digits. That would be pretty bad use of time, I would say. God, if nothing else, we could show you how to do it in Excel, you know? But to add those up, all I actually have to do is go, oh, it's 1,000 times, and I'm gonna go a little faster here, 1,001 over 2. That's 500 times 1,001, and I believe that's gonna be 5,005. Let's see, so it's 500 times that, so yeah. I just added up the first 1,000 numbers just with that formula. So we're gonna prove that this formula is true no matter what n is. And the way to do that is with induction. But first, I wanna tell you a story. Have you heard of Euler? Euler, you've heard of Euler? Yeah, like one of the greatest mathematicians of all time. Got a number named after him, that E that I talked about last time. Euler was like when Euler was a baby, Euler came out and proved this formula. Just like on the not operating table, like right in the birth room, whatever. Popped out into a little pan and then proved this. He might have been 7, but he was young. So one of Euler's teachers said, hey, what is the sum of these numbers? And Euler was so smart and had such deep insight that he said, well, wait, and all the other kids are like, you know, they didn't even have calculators, right? And Euler said, well, wait a minute, whoa, look at this. If I actually write these numbers backwards underneath there, let's write this one out. So there's 99 plus 100, so this would be 2 plus 1. So he wrote the sum backwards underneath and said, okay, well, let's add straight down. So this is 101 plus, what's this gonna be? 101. What's the next one gonna be? 101. 101. 101. How many of those 101s are there?
100.
100 of them. So he said, okay, well wait, that's just 100 times 101. But notice that I've actually added all those numbers twice, right? So I've literally done the whole sum twice. I've added 100, 1 plus 100 plus 1 plus 100. So this is twice as much as I need. So just divide by 2. Cranked it out, 5,050. Because that's 50 right there. You can just cancel that out. That's a kind of genius, to just be able to see that rhythm in the universe and then apply it instantly. So, do you see how this is actually our formula? Check it out. What's n here? 100. So if n is 100, this is our freaking formula. It's 100 times 100 plus 1 over 2. I think that's pretty amazing. That's really cool. So there's another justification for why that we should believe this formula. But what we're going to do now is proceed to prove that it's true no matter how many we're adding up. So this is going to be lots of little side notes and stuff in it. And when you write this out, you're going to have a much cleaner version, which I'll show you right after this. So this is going to have like notes like note this and little side notes that you won't want to put in your proof. So first off, step 1 is establish a base case. And what I mean by base case over here is we're trying to prove that this statement, whatever this thing is, so right now, this is P of n right now. So just make a little note. That is the P of n I'm talking about. It's a statement that can be true or false, and it really just relates to this entire equation that we're trying to prove. And I'm trying to prove it's true for, where's my lowest n? It's b. So check it out. This case right here is just for n equals b, then b plus 1, b plus 2, forever. There's kind of something really deep going on here because we're trying to prove something about infinitely many cases. That is like a heavy philosophical thing. Like, is it even possible to talk about an infinite number of things? What does that even mean? We're not going to get into that. But it's a really fun mathy question and philosophical question. Does this statement make sense right here? Just let me know if that makes sense. I'm seeing some nods.
Why do we have to substitute n for b?
So looking at this,
B is your base case?
yeah, B is going to be our base case. So we're saying this is true for all n after some cutoff point, Yvonne. And so I'm just saying here that n is going to start at that cutoff point. So like if B was 5, then this would be 5, 6, 7. So this would be like B equals 5. So I'm just kind of really trying to express this thing here in a slightly different way.
Okay.
Does that help?
Yeah.
Okay, all right, cool. So really for us, and I should have put this here. I forgot this. I'm so excited about all of this. For n greater than or equal to 1. That's what we're trying to prove for. So add that, please add that to the statement, because here our b is 1. That's our base. So for 1, 2, 3, 4, 5, this is true. Okay, so establish a base case. Use your lowest possible value of n and plug it into the formula. So this is the kind of stuff you're not going to put in your proof. Plug it into P of n and show that it's true. So my lowest case here, n is equal to 1. So I'm going to plug this into my formula. So P of n is that statement right there. What does that statement look like? What does P of 1 look like? So I'm using this colon here. What is P of 1 if that's P of n? What's the left side?
1.
1, just 1, right? It doesn't go any further. If n is 1, we're already starting at 1. There's nowhere else to go. So the left-hand side, so this is the left-hand side, LHS, is equal to, what does the right side look like? Like in terms of a formula, I want to write that all out. What do I write over there? Yeah, but not, so what is it? Yep, you're exactly, but what is n for right now?
1.
Just 1, right? So it's going to be 1.
1, parentheses, 1 plus 1.
Beautiful,
And then
good
over
stuff. Over 2. And what does that right-hand side equal?
1.
1. So then I put, this is equal to 1. So I put a little check mark and I say true for n equals 1. So I have to set up some base truth. And then what we're kind of going to do is use, it's like a ladder. So we have like a ladder, and this is the base is the first rung. That's our base case. Now what we're going to prove is what's called the inductive step. And the inductive step is I'm going to prove I can actually move from one rung to the next rung. So the inductive step kind of takes place up here at the kth rung, and we're going to show that we can, if this one's true, we can move to this one and it's true. So this right here, I'm going to put a little note. This is the inductive step. cool. So folks who aren't writing notes, that's cool. I think it's good. No, and I don't want you to, because I want you to like focus if that's what helps you the best. But you're gonna want to like go back through the recording when you do your proof, and follow these steps, right? So I want to be present. I'm with that. I'm all for it. Yeah, don't start writing shit just to write shit. You don't need to put on a show. I want you to learn. So, base case established. Now I'm going to put my P of N back up here and make sure we've got it. So let's just put P of N back up here. Notice how I write P of N colon 2, 3. That's what I want to show. So the next step, step 2. This is the inductive step. And in the inductive step, we're going to assume that P of K is true for some K. We don't even know what. We're just going to replace N with K for some K that's in our appropriate range. And show this forces the next case to be true, the next rung on the ladder. I'm going to assume I'm at one rung on the ladder and prove I can always get to the next rung. This forces P of K plus 1 to be true. This is just about it. It's really kind of a two-step process. This is where your math is going to come in. This base case here, I hope to hell we can all do this, because this is literally plugging a number into a formula, right? So there's not really any thinking happening here. We could actually write a program to do step 1. We can't write a program to do the next step. That's where our humanity interfaces with the math. So here, I'm going to write out P of K is the statement. And again, I'm going to do a couple examples where I write this all out exactly the way I want you to write it out. Is the statement 1 plus 2 plus 3 up to K. Hey, what's right before this? If I wanted to add another term here, so like, what comes right before K?
K minus 1.
K minus 1. So check out the rhythm. You're going to be a computer scientist, and rhythms are like what your bread and butter is, like understanding patterns. And right before this would just be one less than the last number. And it's really important to be able to understand that, because sometimes the next step can be a little tricky. Equals K times K plus 1 over 2. So I'm assuming that, so assume this is true. Somehow I have to get to P of K plus 1. So let's make a little note here. Note, P of K plus 1 would be, let's write out what that is. So we've got where we start. I want to write my target out here. I'm going to put where my goal is so that I have it in mind as I proceed through this. P of K plus 1 would be 1 plus 2 plus 3 up to, so when I say this, I'm replacing N with K plus 1. It's a function. So you literally just kind of just replace it. I would use parentheses, better than I did there. What comes right before K plus 1 in this rhythm? K. Yeah, we get it, right? So the K comes there. That's really important to see. K plus 1 equals, and then I'm going to go to that formula and replace N with K plus 1. So I got K plus 1 times K plus 1 plus 1 over 2. And then I'll do a little simplification. That's K plus 1 times K plus 2 over 2. So what I need to show is that this is true. This is my goal, to get this statement. And I have to get that statement only by assuming this is the truth. So let me give you a second to just process that. Just make sure you're with me. Because the next step is the gusto step. All right. So here's the truth we have. Here's the truth we want. So I'm going to start with that. Start. So this is algebra time. Was that a yeah? Was that an oh yeah? Did somebody say oh yeah? No.
It's a fake gag.
It was a fake gag. Oh.
Don't do it.
It's gonna be a rough road for the next week. Algebra time. Start by writing P of K and leave some space. And I'll show you what I mean. So I'm going to rewrite this statement, but I'm going to leave a little space right here between the left side and the equals. So leave some space to the left of the equal. And so what that's going to look like is this. 1 plus 2 plus 3 plus blah, 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 plus k, leave some space, equals. And then write this right-hand side. That's true. I know that that's true right now. I'm assuming that's true anyway. What do I need to do? How do I modify this statement, the left-hand side, to make it look like the thing I want? What do I need to do to this left-hand side to make it look like my goal statement?
Add k plus 1.
Add a k plus 1. Is everybody seeing that? I mean, you might be like, oh, that's really obvious, but it will maybe be less obvious in the future. So I just need to add k plus 1. So here, I'm going to add k plus 1. But you can't just add stuff to an equation on one side. You have to do it to both sides. So I'm going to add k plus 1 to the right. So now check this out. The motivation to add k plus 1 was to make this left side look like that left side. And then I have to be lawful, mathematically, and add k plus 1 to both sides. Okay, so get with me. Good, all right. So now the left side looks like my goal, right? The left side is like solid, I'm done. I have to manipulate the right side and show that it's actually this formula. So now I'm going to manipulate the right side using some not terribly complicated algebra, but I'm going to literally just add these two things together and simplify. And then, hope to hell, it looks like k plus 1 times k plus 2 over 2. And if it does, I've proven the statement. So let me write out what I just said there. So you have this, not just in your notes, but I do want to leave that. Add k plus 1 to each side. And manipulate the right-hand side, RHS, using algebra to look like the right-hand side of the goal. And if you have to pop a PBR to do that, do it. Nice afternoon beer, right?
Good in-class beer.
Wait, is that a White Claw?
No.
Okay, all right.
They go over 102.
It's a White Claw
first.
allowed.
All right, so basically I just have to manipulate that right-hand side. So I'm going to rewrite this again. So I'm just going to copy this down. You would write this underneath that. You wouldn't need to rewrite the left-hand side, but I'm going to. So I'm just actually just recopying all that. You don't need to do this because unless you need space and you're moving to the top of a new page. How do I add those two things together? Help me out. Joey, you were in calculus for crying out loud.
Common denominator?
Have you had calculus?
Yeah.
Okay, there you go. You didn't mean calculus though, did you?
No.
No, because this is like much earlier than calculus, this fact. To add fractions, we need a common denominator. Yvonne, you seem to be a man who really knows fractions. What's the denominator I should be getting or shooting for?
Well, you could do like 4.
I could. Sounds like a little bit of overkill. What's the denominator on this? Yeah. So you could.
But no.
But no. So realize that this is actually a fraction that's just over 1.
Yeah.
So when you have something that doesn't look like a fraction and your heart wishes it was a fraction, make it a freaking fraction over 1. Now, Yvonne, what's a much better LCD, least common denominator?
2.
There we go. We're gonna make it 2. How do I make this a 2? Maybe somebody besides Yvonne knows fractions. I know some folks here are saying things to me. How do I get a 2 in the bottom here? What do I have to do? Anybody?
Divide by 2.
Divide by 2 and also multiply by 2, right? So top and bottom times 2. Because I think, did you say divide by 2, Tracy?
Yeah.
Yeah, so just make sure you multiply by 2 on the top and that's perfect. So when you modify a fraction, do the same thing to the top and the bottom. So this is gonna equal k times k plus 1 over 2 plus 2 times k plus 1. Check out those parentheses, they're sweet. So top and bottom get a 2 on them. And now I can bring them together. Oh my goodness. So at this point, depending on how sophisticated your math eyes are, you could be done in the next step, but you don't have to be. Can somebody give me a hand on how to proceed here? And I'll show a couple different ways. Because I still don't, it doesn't look like this, right? I want this. K times k plus 1 times k plus 2 over 2. I want that formula. Somebody help me out here. Somebody besides Yvonne, he's lifted enough fractions today. Help me out.
Are you gonna have to use the 2 and multiply first?
Could do that. We could definitely multiply that all through there. We could definitely do that, and I would multiply this cat. So let's go 2 different routes. Oh, Tracy, yeah.
Wouldn't it be k squared plus 3k plus 2?
And yeah, exactly. So let's go this route. Beautiful route. Nothing wrong with that. So we're gonna, and I think that's where Vincent was headed with this, multiplying that out. But notice that you can multiply all the way through. It's k squared plus k. Multiply the k in each of those, plus 2k plus 2 over 2, and then, like Trayson just said, combine like terms. What's next?
Foil.
Defoil, right? Exactly, yeah. So factor it. Yeah, exactly. And Cadence is right. You gotta do foil. You gotta think foil, but you gotta think foil
I
backwards.
wonder what it'll look like.
I can't imagine, yeah. So like, did you hear what, there's some wisdom coming out here. He said, I wonder what it'll look like. Well, what do you fucking think it'll look like? I mean, the problem says do it. You know it's doable. If the problem said, is it possible to show? Then you know it's not possible to show. So like you're in school long enough to know how the game of school works. When you're told to do something, it can be done. So yeah, gee, I wonder what it could be. Notice how when I FOIL, I get k squared plus outer is 2k plus inner is 1k. Oh my goodness, right there, plus 2 over 2. Done. We are done. So like use some simple, use the psychology of the problem to help you, but you still have to show this stuff. You can't just like go, and clearly this is the right-hand side. I want you to show me some algebra that leads up to the golden moment. So, now we're done. So this shows, this demonstrates, and you gotta write these words. This demonstrates pk plus 1. And then we have to add a few more words at the end to complete this. And I'm gonna show you a slicker way to do this that is really nice, and it just gets us there without factoring or defactoring or anything. I don't think I've ever said defactor before, but Caden's brought me there. So I'm there now. This demonstrates
Defoil.
defoil, is that, yeah, defoil it. So this demonstrates pk plus 1. So by mathematical induction, by mathematical induction, and you don't have to capitalize it, I'm getting very formal. The statement is true. The statement, maybe, P of n is true. And so your proof will have to end with that, and then you can put some flourish, whatever you want. You can write QED, whatever. Sometimes this, sometimes people do a little closed square. Whatever, you can do this.
That one makes sense more than the other kind of proofs.
I think so too. It's very algorithmic, right? Mm-hmm. It flows top to bottom. Yeah, I agree. For me, this feels like Python. We were talking about programming languages either. This feels like a top-down programming language to me, where the other modes of proof are object-oriented. And I've got inheritance and classes, and I don't know what's happening anywhere. So we've got a nice, clear plan. Let me show you another way to see this really quick. So check this thing out. This is just, let me show you the form. This is k times something plus 2 times the same something over 2. I can actually just factor out that something. What's in the box? K plus 1.
Oh, what the?
Do you see? The box here is this.
Why did we do all the extra steps then?
Well, because I was letting you guys lead me. I let you drive. And you wanted to take the scenic route, you know? Do you see this slicker route though?
But would you allow that?
Oh, I would love that. Like, that would make my heart flutter. Yeah, I would love that. That's totally legit. As long as I believed you. So you'd still have to get to hear cadence, and that would, yeah. If you got to hear and did that, does that make sense? Yeah.
What does the other k plus 1 give? Because there's 2 of them there, and then there's already k.
So I'm factoring, so think about, so what I'm doing here is using the distributive property backwards. So check this out, then, since I appreciate your question. If I wanted to multiply k plus 1 times this thing, I could do k plus 1 times k plus k plus 1 times 2. So you treat this like it's like if this were a 3 here, you'd be like 3k plus 6.
Yeah.
So I'm just using that k plus 1 like it's a solid object, going that times that, plus that times that, and I'm doing it in reverse. So I'm going from this to this and factoring it out. So notice here that if I take this, k plus 1 times k is that, k plus 1 times 2 is that.
Okay.
Is that, yeah? Yes. Yeah, go. Awesome. All right, let's do another. Let's do it without all the little side notes and so forths and et ceteras. So the next thing I want to show is this statement right here. Prove, get rid of that. Prove that 1 plus 2 plus 2 squared dot 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 plus 2 to the nth power. So I'm adding up powers of 2. This is like all in your wheelhouse. This is binary stuff right now. This is like powers of 2 are where computers are happening. Is equal to 2 to the n plus 1 minus 1 for n greater than or equal to 1. That's the thing I want to prove. And so now I'm not going to write all the side notes. We're just going to like go through and roll with it. So, proof. You always want to tell people what's happening in a proof. We're going to know that everything we're doing is induction, but I'd like you to write this. So right now, what's about to happen is what I want you to model your assignment for Monday on. Okay, so please model on this. I'm saying that to the camera, you watch this. Please model it like this. Any other form of doing this is not what I'm asking for. So thank you. You watching this right now. No shit, I'm not lying. So first off, we write base case. What should I use for n for my base case? What's the lowest value of n this is supposed to be true for? 1. So base case, let n equal 1. Oh shit, sorry. Okay, I should have, hold off, proof. First we have to identify P of n. So first up, apologies. Sorry, Cadence, I know you're taking notes there. Whoever's taking notes, Trayson's writing shit down, sorry, apologies. Vincent's writing stuff down. Kyle's writing stuff down, sorry. Or maybe, you don't have to start writing stuff down just because it's assume that P of n is the statement. We need to clarify that so that we know what we're talking about. So we're like, defining our variables in this piece of code that we're writing. Is the statement 1 plus 2 plus 3 plus 2 to the n equals 2 to the n plus 1. When you write proofs, you say a lot of things over and over again. You might have noticed there's a lot of redundancy. That's okay. A proof is a communication. We're trying to explain something to someone. So it's an argument. So assume that. Now we got that. Cool. This is basically labeling things. All right. So now base case. Let n equal 1 because 1 is our lowest value that n can be. And then right underneath that, P of 1, I'm replacing the n with 1. And I put a little colon. To me, this means looks like. Or you could even write a sentence here. P of 1 is the statement. You can write that out if that makes it make more sense to you. That's totally cool. What does the left side look like? What does the left side become when n is 1? So a little bit more.
1 equals.
So 1 plus what's the last thing?
Plus 2.
To the
1.
first. Yes, ma'am. Yeah, exactly. So check it out. It's 1 plus 2 to the first power. Right? Because I've got n equals 1 here, and that becomes a 2. And so it's actually kind of just this version of things. It's 1 plus 2. This is when n equals 1, it just looks like that. Let's stop and make sure everybody's with that. And so then the right side becomes 2 to the what power? 2, right? So does everybody see that's 2 because it's n plus 1, and n is 1, minus 1. And so I write that, and then underneath I'm going to simplify. So this left-hand side is 3 equals 4 minus 1, 3 equals 3, check. It's true when n equals 1. We have a first rung of our ladder. We're solid. Okay, so let me just stop. Is everybody cool about what I'm doing, and any questions on this? Good? Good. Okay. So now we go to the inductive step. We're going to assume P of K is true, i.e., like your proof will actually have all these words. The only thing that's going to be different are the computations, but all these words should be in there. Assume P of K is true, i.e., that 1 plus 2 plus 2 squared plus 2 to the K, sorry, is equal to 2 to the K plus 1 minus 1. The next thing I'm gonna write is what I want to show. And we're gonna write that formula out. This might take a little scratch work. I would ask you to do this as scratch work so you get a nice clean one. We want to show that P of K plus 1 is true, assuming P of K is true. Yeah, it's gonna be a lot of writing. So many worse things in this world than writing, right? If we're bitching about this, man, we are in a truly privileged position if this is the worst thing happening in our lives. That's like the pinnacle of privilege, when this is the worst thing happening to you, writing sentences. So we want to assume that a P of K is true. So I want to see all these beautiful words, and I know you all can do it. I.e., assume, and I'm going to write out P of K here. Sorry, nope, back up. I.e., we want to show, because we already wrote P of K, want to show, and I'm going to replace N with K plus 1 in that top line over there. So I got 1 plus 2 squared plus 2 to the K plus 1 equals, and I'm going to replace on the right side, what does that exponent become when N is K plus 1? What does it simplify to? Top right, when I replace N with K plus 1, what do I have?
K plus 2.
Thank you.
Yes, ma'am.
K plus 2 minus 1. Notice that minus 1 is outside that exponent. That's after you raise the 2 to that power. I want to show that. All right. So, start with the thing we're assuming is true. And leave some space. This is where you're going to leave a little space. So I'm taking the P of N and I'm leaving a little space to the left. What am I going to add in here? To make this look like what do I want, what do I have to add in here? Tea time.
2k plus 1.
What was that?
2k plus 1.
2 to the K plus 1, beautiful, thanks Joey. I'm just gonna add this because does it make sense that that's actually the next term as well?
Yeah.
Right, because that exponent's just bumping up by 1 each time. And I can't just do it to one side, can I? I have to add it to both sides. So plus 2 to the K plus 1. And I'm gonna put a little note here. In parentheses, I'm gonna let the reader know that I add 2 to the K plus 1 to each side. The more you explain, the happier your reader will be. I'm your reader. Okay? So like the more you explain, the happier I will be, and that's good for everybody. To each side of PK. Cool, so the left side is basically done. What can we do? So now it's algebra time. Now I'm gonna do some algebra. Let's help me out here, for God's sakes. I'm gonna get a stool. Take it easy, because it's your turn. Tell me some algebra. Regale me with your tales of combining things.
For exponents, because they're the same, you just add the exponents together?
If I was multiplying, I would add the exponents, but you are right, Sophia, that these are identical, these are the same, right? So the best I can say, we're gonna do what you said with the exponents, but not yet. So Sophia's noting that this and this are the same. So that right-hand side is actually 2 of those minus 1. Notice there are 2 of those 2 to the K plus 1s. Let me know if that's cool, if that needs explanation. Yeah. So now, Sophia, I loved your idea. What's the hidden exponent on this that's not written?
1.
1. So this is actually 2 to the first, right? And now we're gonna do what Sophia said, and I'm gonna add exponents because my reader wants to know what's going on, the inside scoop, and what do I get as my new exponent? K plus 2 minus 1.
Oh, that's crazy.
Are we done?
You can just add exponents together like that.
When you multiply, so that's a great question, Kate. So if I have like some quantity to a power A times that exact same quantity to the power B, then I can add exponents when I multiply.
But it stays as the pivot as it goes forward.
Exactly, yes, yeah. So then I can add, but it has to have the same base. So let me get that up there because you wouldn't want to put that in your proof. This demonstrates the inductive step. How about we just say that? That's a slick way to say a lot of words, a lot more writing in less words. This demonstrates the inductive step, and the result is true. How do we feel about that? And then, your favorite, something like that, or what is the anarchy, whatever you want. Put your favorite sign there as long as it's in good taste. It's all good.
Pentagram is good taste.
It is good taste. Yeah, absolutely. Spent a long time trying to be a wizard when I was younger. So, yeah. Danielle, I got to hear a year load of that the other day in calculus, so.
You're a wizard, Tim.
And so I became a mathematician, as opposed, that was it, that's kind of what it's kind of the same thing. Yeah, so like, all the math writing and the symbols looked like magical sigils to me. It looked like magical writing. And so I was like, okay, this is close, do this is good, I can get money this way.
This is how he brainwashes us all into becoming math majors.
Yes, it is, and then, I'll go home. And, light a little brazier and make offerings to Pythagoras. I'll summon Pythagoras. Yeah, let's try one together.
Really creepy shrine in space.
Yeah, it's gotta be creepy.
Why it's covered.
It's gotta be creepy. Oh, let me show you one last example. And this is why it's really important to make sure you're anchored with that first rung base case, because sometimes if you don't have that, you can prove shit's true that is not true. So let me show you an example of the essence of, or the essentiality, maybe that's a word, of the base case.
Necessity.
The necessity, thank you. There you go. Thank you, sir. All right. So, example, last one of the day. The base case is essential. So, prove, and I'm going to write something that's a lie. We're going to know it's a lie because we just kind of showed it was a lie. Oh, wait. Okay. Oh, what was the thing I asked you to prove? That's the thing. I'm gonna make that a lie. Okay, yeah. 1 plus 2 plus 3. Oh no, because then that'll give it away. I can't do that.
I love the proof on the spot.
I know. Jeez. Okay, let me think. Oh, yeah. Okay, I got it. Prove 1 plus 2. I will. The challenge is accepted. The gauntlet has been tossed. So 2 to the k plus 1 is equal to, here, let's just make up a total, n plus 1 is n times n plus 1 over 2. Now we know this is a lie. let me make sure my first base case is gonna work for n equals 1, so hold on. When n equals 1, not really, no, it's not gonna work.
I just wrote that.
What's that?
So I just wrote that.
Life gets harder each day, doesn't it? What will you do now?
That base case works, doesn't it?
Does it when n equals let's see, so when n equals 1, no, because I get
1 times
'Cause
2
you're gonna get
divided by
1.
2.
I get 1 over here though, right? When n equals
Yeah,
1?
and you get like 5 on the left for now.
What can we do to make, oh, let's make up a bigger line. Let's try here. Let's see, what can I do? When n equals 1, what would make this side, oh, there we go. That'll work. That'll work. Do you see cadence though before, like how that's not gonna, yeah. So for n greater than or equal to 1. So we check our base case, which we just rigged. We rigged this completely. So base case, I'm not gonna go through all the formalities. The base is we're gonna let n equal 1, and so the left-hand side will look like this. The left-hand side is gonna be 1 plus, that's it. When n equals 1, I just have 2 to the 0, I just get 1. The right-hand side is going to equal 1. So it looks like a go. Here. Looks like a go.
Wouldn't it be 1 plus 1 on the left side?
So when n equals 1, what's the exponent on here?
0.
0.
Anything to 0, 1.
So 2 to the 0 is 1.
Yeah.
So this thing's a little bit different. It's so like here, let me show you what I'm talking about, Yvonne. So like if n was 2 on the left side, I'd have 1 plus 2 to the first power. If n is 3, I've got 1 plus 2 plus 2 squared.
Yeah.
So when n equals 1, I really just get that 1.
Okay.
Does that, yeah, do you buy that?
Sure.
I don't know if you buy it.
Yeah, we'll go for it.
Do you buy this?
Yeah.
So when n equals 1, I really just have, this is, here, this will help.
Okay.
Yeah, okay, I thought that would help. Yeah, okay, awesome. So it looks like a go, right? And then I could go through this proof. Let's assume this is true. Assume this is true. So let's do our inductive step. We're going to assume, oh, God damn it. This isn't going to work. Cadence, well, how dare you challenge me to do something on the spot that I haven't prepared?
We believe in you.
Yeah, I know you do. I know you do. Okay, we're gonna look. Sorry, this is fucked up. Sorry, folks. Sorry, Vincent. I know you wrote it in pen.
I just have to change like one little thing. I can just scratch it
Okay,
off.
okay. Well, you're gonna have to change it all now. Yeah, this is a big old scratch pile here. Okay, let me just look up a certain formula. I'm not gonna look up the proof, but what time is it? Oh, I got plenty of time. Sum of cubes. Sum of cubes formula. Oh, sum of cubes. Induction. Look like a really old. I'm looking at it like this. It's like, yeah. What? Oh wait, that's a video. I don't want a video. Now I'm really feeling like a grandpa. Here we go. Okay. Here we go. Okay. So prove. So this is still bogus induction. Prove 1 cubed plus 2 cubed plus blah 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 up to n cubed is equal to damn man, I don't know. We're gonna have to call it a day, and I'm gonna have to do this again. My example is completely screwed. Okay, no, hold on. I'm gonna look up a new example. This is like what I wanna do, and you'll see in a minute, like what I'm wanting to do is just not working. And the thing that I was gonna do is the problem that I gave you, and I didn't realize that. So I apologize for the snafu. So in induction, watch, I'm gonna, induction fail without base case. This is good, this will be all on video. You're gonna enjoy this, Abraham. Check this out. Here we go. Now I'm in Reddit. Oh, you know it's gonna be good.
The rabbit hole.
Yeah, it is.
Somehow gets redirected to QAnon.
I will block that shit. Okay. Sorry if there's any QAnon believers in there.
Damn it!
I'm sorry you're insane.
I was actually that guy with the Viking head.
Yes. Yeah, okay. Alright. Oh, fuck it. Oh, here's some, okay, this will work. Okay, let's try this. There we go. Don't write anything down yet, okay? Do me a favor, do yourself a favor. Let's just say we were trying to prove 1 plus 2 plus 3 plus n equals, and this formula that we already know, we're gonna change it over to, okay, Reddit, save my ass. All right, let's say we're gonna try to prove this for n greater. What are they talking about? That's not even true for n equals 1. It's not true. Oh, okay, yeah. All right, let's try to prove this. There we go. This is gonna work. Don't worry, Yvonne, I found one.
It is?
You're good. This is gonna work. It's not true, but I can prove it with induction if I don't look at the base case. So, prove this. Let's forget the base case. And let's say here we're doing for n equals 1, 2. Can you see it's false for n equals 1? Yeah.
Yeah.
Like the left-hand side is just what?
1,
1, and what's the right-hand side?
0.
0. So notice that the base case would fail. Let's forget the base case because we don't need that. And skip to the inductive step. Whew. Alrighty, so we're going to assume P of k is true. In other words, 1 plus 2 plus 3 plus k is equal to k minus 1 times k plus 2 over 2. P of k plus 1 looks like 1 plus 2 plus 3 plus, and now instead of going to k, we move up one more step. And then the right-hand side, I would replace every k with k plus 1. So what would this become? This term right here, if I replace k with k plus 1.
Okay.
K. And then what's this one going to be?
K plus 3.
K plus 3, beautiful. Over 2. So this is what I want to try to aim for in my goal. So we're going to take this statement and I'm going to add k plus 1 to both sides. So add k plus 1 to each side of k to get, let's do it, 1 plus 2 plus dot 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 plus k, and now I leave a little space and I'm going to just write the original down. And I'm going to add now k plus 1 to each side. And I'm hoping that the right side simplifies to that. So let's see, because right now I don't know if I believe it. What's my common denominator? Tracy?
2.
2, yes, yes, 2, exactly. So I need to get this to be 2 over 2, right? So this is, I'm sorry to harass you, Casey. I knew you would know the answer. Just hearkening back to our old days together in early inductions. So then this is going to be over 2, we've got k minus 1 times k plus 2 plus 2k plus 2. I'm going to start multiplying some stuff out. I distributed that 2. Now I'm going to FOIL some stuff because I don't really see any slick factorings like I did before. So let's see, so this is k squared, outer is 2k, inner is minus k, last is minus 2, plus 2k plus 2, all over 2. Okay, so what does that simplify to? Let me pick it up on the top over here. I will never read Reddit again if this doesn't work out. That's a complete lie. I love Reddit. So let's see, so that, what is that right-hand side? So we've got a k squared. How many k's do we have net?
1.
4.
Wait, just 1,
3.
looks like 3, right?
No, 2.
3, yeah. Right, because we've got 2k minus k, that's 1k, plus another 2k, it's 3k. And then what's the constant at the end? None, right? 0. Oh yeah, Reddit. 0 over 2.
Oh man.
Oh shit, this worked. Do you see? Do you see?
Yeah.
Yeah. So this is k times k plus 3 over 2. Yay, it's true. Induction's true. Well, no. Because that thing doesn't even work for its base case. So this is an example of if you don't check the base case and try to induct, you might believe things that are lies. So, but had we checked the base case, the simplest base case, n equals 1, we would have p of 1 as the statement 1 equals 0, which is a lie. So this is an example of the importance of of checking the base case. Importance of checking the base case first before inducting. Whew, man, that was scary. It's always scary when you're like up here doing stuff, you know, like putting on your show and you like think your show's in order and then you realize you don't have some of your props or you brought the wrong props. Yeah, so.
Then you find a new prop on Reddit.
Yeah, then you're searching the internet desperately for one. But this worked out really good. So that's all. So that's all I got for you today. We have an assignment. Does everyone understand? Almost everyone understands the assignment. I'm positive. One person has not seen the assignment.
The Monday assignment?
The Monday assignment, right? Yes, sir. So you're going to come in. You're going to make a copy. You're going to write a really nice proof like that second one I did, modeling the language and all that, and then I'm going to give you another one because some people will probably be like really tight with that, and then I'll just give you your second one, and some people will work together to get it going. Does that sound okay?
Yeah.
And you'll probably be done by the end of the day on Monday with everything. All righty, my friend Vincent, come here, my friend. Need to give you your assignment. Let me stop this.